can start.
Good morning, everybody. It is my pleasure to introduce Sisam Shrestha, who is a fifth-year PhD candidate advised by Brian Soden. Sisam completed her Bachelor of Science in Atmospheric Science at the University of Louisiana Monroe. She loves to cook, try new recipes, and work on the tiny vegetable garden on her balcony. In spite of the relentless heat and humidity, which has killed everything I've tried to grow here, Sisam has grown bell peppers, mint, cilantro, Thai chili pepper, rosemary, spring onions, and spinach. This is Sisam's final Compass presentation. She will defend her PhD this June, and then head north to Princeton University and the Geophysical Fluid Dynamics Laboratory to start as a postdoctoral researcher. And without further ado, Sisam.
Good morning, everybody. Thank you for coming to my talk this morning. In today's talk, I will go over the work that I've done in the past 5 years with my advisor, Dr. Brian Soden, along with my collaborators and my co-authors. My talk, titled The Analysis of Large-Scale Changes in Large-Scale Atmospheric Circulation During the Satellite Era, aims to study how large-scale circulations have evolved in the past 40-plus years, and can we explain this using theories established on large-scale circulations response in a warming world. We know that large-scale circulations, specifically the Hadley circulation and the Walker circulation, play a vital role in distributing moisture and energy around the globe. The Hadley Zone in 2006 work provides a hydrological constraint on how these large-scale atmospheric circulations are expected to respond or specifically weaken in a warming world. This plot here in particular shows the change in near-surface specific humidity on the left plot and precipitation on the right plot, both of which increase with global mean warming. However, notice that near-surface humidity scales with Clausius-Clapeyron and increases at a rate of around 7% per Kelvin, whereas precipitation increases at a much smaller rate of around 2% per Kelvin. Now, this discrepancy of increase between these two variables is very important because precipitation in our atmosphere can be understood as a product between convective mass flux and near-surface specific humidity. Thus, this differential increase between precipitation and convective mass flux requires a weakening of, precipitation and near-surface specific humidity requires a weakening of the convective mass flux. Now, the problem is that most of the past studies that attempt to analyze changes in large-scale atmospheric circulations have heavily relied on reanalysis dataset to draw their conclusions on how large-scale atmospheric circulations have evolved. A big problem with using reanalysis dataset is the biases that they have or the discrepancy that they have even amongst datasets, especially regarding moisture variables, which in this case from Dester and Davis shows the trend in specific humidity for a multiple reanalysis dataset. And depending on your choice of reanalysis dataset, specific humidity can either increase with global warming as you move up in the atmosphere, or even decrease as shown for the NCEP reanalysis dataset, more so for the tropics, represented here by the black bold lines. This discrepancy amongst reanalysis datasets stems from a number of different possible reasons, one such being the heterogeneous data assimilation that goes into constructing these reanalysis datasets. Thus, the primary motivation behind our work is to analyze how large-scale circulations have changed during the satellite era, during the historical period for which we do have observations, and also to devise an observable proxy that takes us away from this heavy reliance on reanalysis dataset. To do this, my thesis is divided into 4 different chapters. Chapter 1 looks at how large-scale atmospheric circulations have evolved over the satellite era. Chapter Chapter 2 and Chapter 3 are more technical in the sense that we use satellite observations to derive a proxy for mid-tropospheric vertical velocity, which can then be used to analyze changes in large-scale atmospheric circulation. Chapter 4 focuses on one aspect of the large-scale atmospheric circulation, that is the ITCZ, and looks at how it has evolved during the satellite era. For today's talk, I will only focus on results from Chapter 1 and Chapter 4, but I'll also briefly go over results from the more technical chapters 2 and 3. Chapter 1, titled The Anthropogenic Weakening of the Atmospheric Circulation During the Satellite Era, begins with the hydrological constraint from Helvin-Soden in 2006 and again shown in Becky and Soden in 2007. This differential rate of increase between precipitation and near-surface specific humidity requires a weakening of the convective mass flux, which is a robust feature across all the models for the A1B forcing scenario throughout the 21st century, represented in this plot by colored lines for individual models. This weakening of large-scale atmospheric circulation is primarily manifested as a weakening in the zonally asymmetric circulation, which, when we focus on the sea level pattern in the tropical Pacific, shows up as a weakening of the sea level pressure gradient, highlighted here for the Eastern Pacific box in the blue shading and the Western Pacific box in the red shading. That is, a weakening in the asymmetric component manifests as a weakening of the Walker cell, shown up here as a reduction in the sea level pressure gradient between those two boxes. Now, things get interesting when we look at how the Walker circulation has actually evolved over the past few decades, which in this plot highlighted, shown from Watanabe et al. 2023, measures the Walker index, that is the strength of the Walker circulation, using the same sea level pressure gradient between the East Pacific and the West Pacific. And surprisingly, despite the global mean warming experience over the past few decades, the Walker circulation shows a strengthening, highlighted as the straight fitted lines in this plot. So this discrepancy between how we understand the large-scale atmospheric circulations to behave in a warming climate versus how Walker circulation in specific has behaved in the past few decades raises this really important question. A big motivator for our Chapter 1 is our understanding of how the hydrological constraint functions with warming fault. So the goal of Chapter 1 is to evaluate the fidelity of model projections of a weakening of the global atmospheric circulation in a warming climate. And we begin our analysis by looking at the CMIP6 coupled models, which in this case shows a weakening of the tropical Pacific SSD gradient along with a warming of around 0.26 Kelvin per decade, which is in stark contrast with the atmosphere models, the AMIP models, which have SSDs prescribed based on observation. That shows a more La Nina-like pattern where there is a strengthening of the tropical Pacific SSD gradient with cooling in the East Pacific versus warming in the West Pacific. This discrepancy in the SSD pattern between the coupled models versus the atmosphere-only models is reflected on their respective circulation pattern, where the coupled models show a weakening of the Walker circulation with weakening of convection along the West Pacific warm pool, the brown shading on the left plot, and also a weakening of subsidence along the Eastern Pacific. Whereas the AMIP models, consistent with an increase in the SSD gradient, show a strengthening of the Pacific Walker circulation. So keeping this discrepancy in mind between the AMIP, which has SSDs prescribed based on observations, versus the coupled models, we run a comparative analysis between different experiments as part of CMIP6 and also between model simulations and observations. We namely use the atmosphere experiment, the coupled historical one, a very high forcing, future forcing scenario, the SSP 585, and PI control simulations from CMIP6. We also use a 100-member large ensemble from NCAR, the CSM2 large ensemble, and a 10-member CAN6 prescribed SSD ensemble, which extends the NCAR AMIP experiment to year 2021. for our observational estimate of the circulation, we use precipitation from Global Precipitation Climatology Project, GPCP. And for our water vapor, we use total precipitable water from SSMI, and which covers ice-free ocean and aerofiber analysis over land and sea ice, which works like Allen et al. 2020 show a similar internal variability between these two datasets. To measure the strength of the convective mass flux, we use the differential rate of increase between precipitation and near-surface specific humidity. For the coupled historical one, consistent with the hydrological constraint, all these models show a robust weakening of larger atmospheric circulations, with individual models in this plot represented by the thin blue lines, and the multi-model ensemble represented by the bold blue lines, with an ensemble mean weakening of around 1% per decade. Surprisingly, even the ANIT models, which we remember has an increase in the Pacific SST gradient, shows a weakening, although slightly smaller in magnitude, over the same 1979 to 2014 period. And this weakening of the convective mass flux can also be seen in our observational estimate, which in both the plots are represented by the red line, and is comparable in magnitude with the ANIT estimate at around negative 0.69% per decade. Thus, both the coupled models and the observations show a mean weakening of the circulation over the common period. Now, the problem is that these experiments for the historical period as part of CMIP 6 only run till 2014, whereas when this study was conducted, we had satellite observations for the up to complete 2021. So the question arises, how has the circulation changed for this additional 6 years of period? And we again start by looking at the SST pattern evolution for these additional 6 years taken into consideration, and we still find that this discrepancy in the SST pattern between coupled models and the observations in the tropical Pacific still persists, with the observations still showing a strengthening of the SST gradient versus the historical coupled ones showing a weakening of the tropical SST gradient. And like for this smaller period of analysis, this extended run with global mean warming shows a weakening of the convective mass flux over this period, again red representing the observed weakening versus blue representing the coupled model simulations, with the observed weakening of around 4% from 1988 to 2021. Now, this spread in the blue lines, that is the coupled models, can be due to two reasons. One, due to differences in model physics, since all these individual lines correspond to different models. And two, due to differences in internal variability. To overcome at least one aspect of this challenge, we employ large ensembles, which have the added benefit of sharing the same model physics. So the differences in large ensemble mainly stem from internal variability, and the ensemble average can be considered as a forced response. In particular, we use the CSM2 large ensemble, which is a 100-member large ensemble sharing the same model physics, but only differing in terms of their internal variability. And we still find this robust weakening of the convective mass flux for the CSM2 large ensembles for all the 100 members, which is also consistent with the atmosphere-only counterpart, the CAM6 ensemble, which extends the prescribed SST ANIT runs to year 2021. Thus, despite differences in the SST pattern, the convective mass flux has weakened both in observations and in climate models, coupled and atmosphere both. And again, to stress the point that this weakening of large-scale atmospheric circulations is mainly due to global mean warming and rather insensitive to tropical SST pattern. In this plot, we regress the convective mass flux on the y-axis against the global mean temperature increase on the left plot, and the SST pattern taken as the difference between the West Pacific and the East Pacific on the right plot. And we find that there is a very strong correlation between global mean temperature increase and the convective mass flux weakening, where models with a stronger global mean warming also simulate a stronger weakening of the convective mass flux. Whereas if you look at the right plot, which shows the tropical Pacific SST gradient, we find that some coupled models do simulate this strengthening of tropical Pacific SST gradient, but there isn't any correlation, or not a very strong correlation, between the convective mass flux weakening versus the gradient in the tropical Pacific SST. Now, the question arises, can this weakening of convective mass flux be explained by internal variability alone? So we bring in our PI control simulations, which have forcings fixed at the 1850 level, so it's just internal variability fluctuations in these simulations, represented in this plot by the black bars. And we find that none of the PI control simulations for this 1988 to 2021 period have a weakening of the convective mass flux as strong as the observed weakening represented in this plot by the red line. Also to be noted in this plot is this difference in the observed weakening and the CSM2 large ensemble mean weakening represented by the green line. However, if we take into account the amount of warming experienced in observations versus simulated by the CSM2 large ensemble, that is, if we normalize these by global mean warming, we find that this observed weakening is very similar in magnitude to the CSM2 large ensemble simulated weakening per Kelvin global warming, and both of these values, both observations and the NCAR coupled models, lie on the higher end of the CNIP6 coupled into model spread. Thus, with chapter 1, we can conclude 4 main points. First being that there has been, for the first time, utilizing a growing record of satellite observations, a weakening of large-scale atmospheric circulation of around 4% from 1988 to 2021. Second, using coupled models and AMIP, which differ in terms of their SSD pattern in the tropical Pacific specifically, both show a weakening of large-scale atmospheric circulation. Thus, this weakening is dependent on the mean warming and rather insensitive to the Pacific SST gradient. Thirdly, we can conclude that this weakening of circulation can take place despite a strengthening of the Pacific Walker circulation, which again we show from using the coupled models, which have a weakening of Walker circulation, versus the AMIP, which have a strengthening of the Walker circulation consistent with their increase in tropical Pacific SST. And lastly, using these 3 above conclusions, we can finally conclude that the theories on drivers of the circulation change still hold true. So that was my chapter 1. Sorry, what a break. So up till now, we were able to confirm that these hydrological constraints postulated using older version of models that were earlier studied using reanalysis or idealized forcing we have actually started to realize this in our observations, and also this still holds true for the newer versions of climate models. The next 2 chapters, which deal with solving this issue of moving away from heavy reliance on reanalysis product, and also at the same time creating this supplemental observational proxy to study large-scale atmospheric circulations, is the goal of utilizing this growing record of satellite observations of around 40 plus years, and is specifically for chapter 2 titled Estimating Mid-Tropospheric Vertical Pressure Velocity from Satellite Observations of Upper-Tropospheric Relative Humidity, which is inspired by works like Bellow and Clement, who've used cloud observations over ocean, and from the ITCZ project, which only begins from year 1982, thus having a smaller spatial resolution, whereas for this specific chapter, we take that work a step further and we use observations from the HERS instrument on board NOAA's Polar Orbiting Satellite, which provides us with a near complete global observation and starts from 1979. So a larger spatial coverage and also a longer temporal scale. So works like Chung et al. 2011 and Tivik et al. 2020 have drawn similarities between upper tropospheric relative humidity derived from the HERS instrument and mid-tropospheric vertical pressure velocity, which in this plot, here I show the climatology for UTH on the top panel and for metrospheric vertical velocity on the bottom panel using the AMIP experiment as part of CMIP6. And we can clearly see that larger values of tropospheric relative humidity coincide with convectively active regions like the West Pacific Warm Pole and along the ITCZ, whereas conversely, the smaller values of tropospheric relative humidity coincide with the subsidence branch along the tropical edge and the Southeast Pacific. So those past works derive similarities between tropospheric relative humidity and metrospheric vertical velocity. We take it even a step further and actually quantify this relation and estimate omega 500 using observations of tropospheric humidity from the HERS instrument, which I show in this plot as the decadal trend of the estimated omega 500 in the bottom, which shows an increase in subsidence along the Central Pacific and increase in convection along the maritime continent, whereas the actual UTH observations that we use to derive the product is shown in the top panel, where the same regions, the Central Pacific subsidence increase coincides with a drying in the tropospheric relative humidity. And along the maritime continent, it coincides with an increase in tropospheric relative humidity. This utilization or application of tropospheric relative humidity, or specifically the HERS measurements, also inspired Chapter 3, which is titled The Observed Trend in Tropospheric Moisture and Its Implications for Water Vapor Feedback. So Chapter 2 specifically looked at relative humidity, whereas in Chapter 3, we look at specific humidity, that is the actual moisture content in our upper troposphere, which is important because, as pointed out in Kelvin Soden, although the amount of moisture decreases as we move above in the atmosphere, it's this logarithmic relation between water vapor and outgoing luminous radiation that makes moisture in our upper troposphere an important factor in determining or studying water vapor feedback. So again, utilizing the HERS observations, we derive a upper-tropospheric specific humidity index which combines different channels of satellite observations and shows that specifically in case of observations represented in this plot by the red line, there has been an increase in global mean moisture in our upper troposphere, which is also simulated by the AMIP experiments as part of CMIP6, again represented here by the black lines, and also captured by our coupled historical runs represented here by the blue lines. Thus, with a warming world, there has been an increase in upper tropospheric moisture consistent with how we understand moisture to increase, or as in accordance with the theories that have been established in past studies. So Chapter 2 and Chapter 3, we created this proxy dataset by using HERS observations for 40 plus years of upper tropospheric humidity. So it got us closer to that goal of moving away from heavy reliance on reanalysis dataset and creating this supplemental observational proxy. But at the same time, it revealed something very interesting, which, as shown here for the HERS UTH dataset, in the blue dash line, we find for the decadal trend, that is blue dash line, we find a shift of the climatological pattern in the deep tropics. That is an increase of the upper tropospheric humidity north of the equatorial peak. A similar northward shift is also seen for GPCV precipitation, the green line, and for NOAA outgoing luminary radiation, the red line, which for easier interpretation in this specific plot, we flip the axis. Which is very important because this northward increase in moisture, which is seen in all these different data sets taken from different satellite measurements, suggests a northward migration of the tropical precipitation band, specifically the Intertropical Convergence Zone, also known as the ITCZ. So Chapter 4 deals with how the ITCZ in recent years has migrated, or has it migrated. And before we move into the results, I will briefly go over the background of the ITCZ and what controls its migration. So the ITCZ, seen as an intense band of precipitation that is zonally oriented in the deep tropics, is annually positioned slightly off the equator in the northern hemisphere, which has been explained by works like Ferguson et al. 2013 as a northward ocean energy transport in the mean state. However, following the solar cycle, the ITCZ can migrate either north or south of the equator. Works like Schneider et al. 2014 have also shown migration of the ITCZ, specifically the meridional migration of the ITCZ in glacial and interglacial period, which for this case they use paleoproxies to locate their ITCZ, represented in this plot by the red line. And we see that there has been a fluctuation in the ITCZ location over the Holocene period for the past 1,000 years. And if you notice, this fluctuation in the ITCZ is also related to the interhemispheric temperature difference. That is the temperature difference between the northern hemisphere and the southern hemisphere, represented by the black lines. So works like Manabe and Stufer 1980 have introduced this idea of the tropical precipitation migrating in response to a temperature gradient between the hemispheres. And then later works like Chung et al. 2003 and Broccoli et al. 2006 followed it by showing this migration in presence of interhemispheric temperature gradient using idealized forcing experiments. And then later works like Kang et al. 2007 and then 2008 provided an energetic framework to explain this migration of ITCZ, which in this plot shows considers a relative warming of the northern hemisphere and a relative cooling of the southern hemisphere. And according to the energetic framework, it postulates that this interhemispheric thermal gradient sets up an anomalous Hadley circulation, which transports energy into the cooler hemisphere from its upper branch, whereas it transports moisture in the opposite direction into the warmer hemisphere from its lower branch, which further pushes the ITCZ into the warmer hemisphere. And that's the schematic. Now, the historical period, specifically the 20th century, has been marked by a southward shift of the ITCZ, which in this plot, represented by the black line, I showed the multi-model mean for 39 coupled models belonging to CMIP6. And the southward shift has also been seen in observations as shown by Wang et al. 2013, and as explained in Chung and Soden in 2017, the southward shift can be explained by the indirect anthropogenic aerosol effects, which for this period of late 20th century is marked by increasing anthropogenic aerosols in the northern mid-latitudes where anthropogenic activities are more prominent, which relatively cools the northern hemisphere and, according to the energetic schematic, pushes the ITCZ further into the southern hemisphere. But the question remains, has the ITCZ shifted even more? Has it gone even more south? Has it recovered and started migrating more north in the recent years? And this question is very important from two different perspectives. First, by analyzing if it has migrated south or north, we test this energetic framework. Does it still hold true for our observations? Considering the fact that there has been a decrease in the aerosols, so the energetic framework, according to the relative warming of the northern hemisphere, would push the ITCZ further into the northern hemisphere. And second, from a societal perspective, the ITCZ, although very tiny, as shown in the map, contributes to around 30% of global mean precipitation. Thus, fluctuations in the ITCZ, especially for the tiny islands lying right along the equator, can mean differences in temperatures going all the way from drying in a specific year versus torrential flooding when the ITCZ migrates closer to that island. So goal 1 of this chapter is to analyze whether the ITCZ has shifted north in recent years. And to do so, we extend our CMIP6 coupled bonds using the SSB 245 scenario. And we find that the ITCZ has in fact shifted north in recent years, that is during the satellite era from 1979 to 2023, at a rate of around 0.046 degree per decade. This particular ITCZ metric, this particular metric that we use to locate ITCZ is the precipitation centroid definition based on Adam et al. 2016. However, if we use an alternative definition to locate the ITCZ location, like the zero latitude of the mass stream function closest to the equator, we find a similar increase in we find a similar northward migration of the ITCZ over this period, with the red cross representing the ERA 5 reanalysis dataset. And this northward migration of the ITCZ that we saw in the coupled models is also a significant feature in the observations based on Global Precipitation Climatology Project, GPCP version 2.3, in this plot represented by the black line, and the ERA 5 reanalysis again represented by the red colored line. And also for our 100-member CSM large ensemble, we do find a northward migration of the ITCZ. Two things to be noted in this plot are the large fluctuations for the 1980 period and along 1998, which correspond for the 1980 period of volcanic eruption, and for the 1998 period, a strong El Nino that pushed the ITCZ further south. But an overall trend shows a northward migration for this 1979 to 2023 period. And this observed northward migration of the ITCZ lies well within the CSM2 large ensemble, and also for the CMIP6 coupled models, with the large ensemble represented by the green bars, and the CMIP6 coupled models represented by the blue bars. So up to this point, looking at our observation data set and our coupled models, we find a northward migration of the ITCZ. Thus, we can answer this question: has the ITCZ shifted north? Yes, it has. But as we all know, the CMIP coupled models specifically have this notorious problem with getting the ITCZ position correct, or specifically having this very large double ITCZ bias. Especially in the Eastern Pacific, where there is a parallel ITCZ running, where there is an ITCZ running parallel to the northern ITCZ. So we want to test out whether what we are seeing in these coupled models in terms of the northward migration has to do anything with this double ITCZ bias. And to do so, we use the Tropical Precipitation Asymmetry Index from Wang et al. 2013, which basically takes the difference between the northern hemisphere tropics, 0 to 20, and the southern hemisphere tropics, and normalizes it by the tropical mean precipitation. So, weaker the TPAI index, stronger the double ITCZ bias. But as we can see from this figure, the ITCZ northward shift does not have a very strong correlation with the models, with the individual models' double ITCZ bias. There are also other double ITCZ metrics, like the equatorial precipitation index, for which, again, we do not find a very strong correlation between ITCZ migration versus double ITCZ bias based on EPI. We do find a very strong correlation, however, with these individual models' interhemispheric temperature difference, consistent with the energetic framework, where models with a stronger northward gradient of interhemispheric temperature have a larger northward migration of the ITCZ, also seen in our GPCB product for the green line and for ERA 5 reanalysis for the red line, which show that the ITCZ has migrated north, consistent with this observed relative warming of the northern hemisphere over this satellite era. And we also find a very strong correlation between this northward ITCZ migration and changes in cross-equatorial atmospheric energy transport, which again I've put a schematic here for easier interpretation. Remember that with the migration of the ITCZ further into the northern hemisphere, the northward atmospheric energy transport decreases or gets more stronger towards the south. And as shown in this figure, we do find that models that have a larger weakening of the northward cross-equatorial atmospheric energy transport also have a stronger migration of the ITCZ towards the northern hemisphere. With again the arrow 5 represented by the red cross and the CNIP6 multi-model ensemble represented by the blue cross. Now we find that for the coupled models, this weakening is this shift is at a rate of around 2.2 degrees of latitude of meridional migration per petawatt of atmospheric energy transport, which is slightly lower but similar to the value put out by Donovan and Voigt 2017. Now, this brings us to the second goal of our work, that is, can we attribute this meridional shift of the ITCZ to a particular forcing agent? Now remember, the energetic framework postulates that increasing atmospheric anthropogenic aerosols in our atmosphere in the northern hemisphere relatively cooled it and further pushed the ITCZ into the southern hemisphere. But following the Clean Air Act of the 1970s, we've seen a robust weakening of anthropogenic aerosols as shown in works like Cross et al. 2022, which would mean that a relative warming of the northern hemisphere would have to push the ITCZ further into the northern hemisphere, which we do see that the ITCZ has migrated, but can we specifically attribute this migration to a weakening of anthropogenic aerosols alone? And to answer this question, we utilize this detection and attribution model intercomparison project, DAMIP, which has the benefit of running the single forcing experiments, namely the historical natural-only experiments that have solar irradiance and volcanic eruptions, which have time evolution of solar irradiance and volcanic eruptions with all the other external forcings fixed at PI control levels. The greenhouse gas only experiment, which again has time evolution of greenhouse gases in our atmosphere with all the other external forcings fixed at PI control, and likewise for the time evolution of anthropogenic aerosols, the HIS-AIR experiment, which again lets us study the effect of the climate variability due to anthropogenic aerosols alone. So utilizing these single forcing experiments, we calculate, again using the precipitation centroid, the ITCZ migration for these three different single forcing experiments and compare it with the all forcing scenario. Represented in this plot for the individual models numbered, the black numbers represent the all forcing scenario, the historical forcing. The blue numbers represent the aerosol-only forcing, the red represent the greenhouse gas only forcing, and the greens represent the natural-only forcing. And we find that all these three different single forcing experiments simulate some magnitude of northward ITCZ migration over this period at similar rates between the greenhouse gas forcing and the aerosol forcing, but at the same time smaller than the all forcing ensemble. Thus, all three forcings in some way has contributed to a northward migration, but not one single forcing, at least from this plot as shown, can explain this northward migration in the coupled models. And again, as shown for our interhemispheric temperature difference, we find that all three forcings simulate an increase in northward interhemispheric temperature difference over this period, with an increase in greenhouse gas preferentially warming the northern hemisphere, which has the larger landmass, a reduction in anthropogenic aerosols represented by the blue models here, which after reducing the anthropogenic aerosols relatively warms the northern hemisphere mid-latitudes. But it's also interesting that even the greenhouse gas, even the natural-only forcing represented by the green numbers here, also simulates some magnitude of ITCZ northward migration and a relative warming of the northern hemisphere, which is very interesting because it has contributed to some magnitude of this overall ITCZ migration. And to understand that, we look at the ITCZ migration represented by the green line for the historical natural forcing only experiment, and the interhemispheric temperature difference represented by the black line, again for the historical natural only experiment. And we can see that these large deviations of the ITCZ position and also the changes in interhemispheric temperature gradient coincide with large volcanic eruption. Especially in the late 19th century, early 20th century, large southward migration of the ITCZ coincided with big eruptions like the Krakatoa and Nova eruption, and also the Santa Maria. Whereas for our analysis period, which begins from 1979 to 2021, it is marked with two big eruptions, the El Chichon in Mexico and Mount Pinatubo around 1991, which pushes the ITCZ more southward from the base state, and thus when we fit a line to it, we find a relative northward recovery from this southward migration following the volcanic eruption. Thus, from this chapter, we can conclude that using observation data set that has extended from 1979 to 2023 period, the ITCZ has shifted northward. And this is a very important point because past works, we looked at GPCB data set to locate the ITCZ, did not find a statistically significant shift in the ITCZ. And that might be the case because they were looking at a comparatively smaller time period to analyze ITCZ location shift. Whereas in our study, we look at 44 years worth of data to study the ITCZ location. But, and also this northward shift is simulated in CMIP6 coupled models. And lastly, this northward shift cannot be attributed to one specific forcing agent alone. A reduction in anthropogenic aerosol, which relatively warms the northern hemisphere, an increase in greenhouse gas, which preferentially warms the northern hemisphere, and also this recovery from volcanic eruption have all contributed to some magnitude to the northward migration of the ITCZ in recent years. Thus, with all these 4 chapters from my thesis, we can conclude that large-scale atmospheric circulations over the satellite era specifically have weakened in presence of global mean warming, consistent with theories that were established using just models. So it's amazing that for the first time we can actually see this effect of weakening of large-scale circulation, and also using PI control simulations specifically attribute this weakening to anthropogenic effects. And secondly, we can also conclude that there has been a statistically significant shift of the ITCZ, which cannot be attributed to one single forcing, but is a response to all these 3 different factors: a reduction in anthropogenic aerosol, an increase in greenhouse gas, and also in some way a recovery from the volcanic eruptions that marks the beginning of the satellite era. And that was my talk. Thank you all for being so patient, and if you have any questions, comments, suggestions, I'd be happy to take them.
You don't really need the microphone, nobody is in Zoom.
So this was a just fantastic talk. You really restated all the points in a really great way. I'm just kind of curious if you thought about this relationship you found with the volcanoes and this sort of ITCZ shift. I know we don't have a lot of data points, but if you suspect there's anything with the location of these eruptions, or obviously the strength of the eruptions and how much aerosols are putting out, if this is something that you've seen in your work or something you've seen in other work that might be affected.
Mm-hmm. Yeah, that's an excellent question. Yeah, thank you. So we do actually see these differences in how the aerosols have been input into the atmosphere versus how the aerosol input has further contributed to a cooling of the one specific hemisphere. Like if we look at Nova Rupture, which was up in Alaska, which relatively cooled the northern hemisphere. So although it wasn't close to the tropical belt, not close to the ITCZ, it did contribute to that, to creating that interhemispheric gradient. So as long as there is some kind of interhemispheric gradient, the energetic framework kicks in and then pushes the ITCZ. And also, I guess, yes, depending on the amount of cooling that contributes to, that is contributed by the aerosol injected into our atmosphere, also shifts the ITCZ further away from the base state here.
I guess we had that recent eruption in 2022, and I wonder if that may have contributed, or if there's any evidence of a shift. I know you probably don't see it in the data, but...
Yeah, we do not, well, at least for the CMIP6 historical natural forcing at this time period, we do not see, I guess, the recent eruption to be that significant, but then maybe like adding more, I guess, data points to those natural forcing experiments consistent with the recent eruptions would show up, I guess, maybe in CMIP7.
Yeah, great work, thank you.
Which Brian?
No, I just had a follow-up question to that because I've never heard of Nova Rupture before. So I'm guessing it's a weaker volcano.
The Nova Rupture was...
compared to Krakatoa or Pinatubo. And so, are you saying that if you have a weaker eruption that's further north or south, that how do I want to say this? The further away it is from the equator, you can still get a shift in the ITCZ with a weak eruption just because it's the aerosol will be more asymmetrically distributed.
Yes, the asymmetry of the aerosol injected in the atmosphere does contribute to the meridional shift of the ITCZ, and so it does not have to be closer to the equator, I guess.
And so then a gun was must injected aerosol preferentially in the southern hemisphere,
Yes.
is that correct?
So if you look at the aerosol optical depth for Aegon specifically, it does have a larger aerosol optical depth in the southern tropics compared to the northern tropics, and consistently a more northward migration of the ITCZ.
Brian, yeah, this is really great. Thank you. If you had to look forward to the next 50 years, do you see, based on what you've done, do you think the global circulation will continue weakening at the same rate or faster, or is there some mechanism that will keep it in check eventually?
So we find that even for our future forcing scenarios, specifically looking at the scenario MIPS as part of CMIP6, we find a weakening. So this weakening signal with warming is a robust feature for all the different scenarios, future forcing scenarios. And we find that it is closer to the value from the hydrological constraint of around 5% per Kelvin. So that seems to be the golden number. But it's, again, like, it's not just a number that comes out of thin air. It's based on the hydrological constraint where the precipitation increases at 2% per Kelvin versus the specific humidity that scales with clouds of Clapeyron at 7%.
Okay, so
Still a weakening.
weakening.
Yes.
So it goes away.
Where's Brian?
I'm Brian all the time. Sorry, and I might have, I'm sorry if my attention drifted. Did you find anything surprising in its sign? Or all these numbers, you quantified things whose sign was as expected?
The sign as in the sign of
Sign of the number. Did you find any numbers, any trends in it? Did you find anything that was surprising in its sense or sign?
I mean, there were a few anomaly models for our, especially in chapter 1, we mentioned it in the paper. There were a few anomaly models, the F-goals model, that have a anomalous increase in the past few decades, but that's more of a model artifact. So yes, I guess that's the one sign change that we did notice during our analysis, where instead of a weakening, we found a strengthening of the mean circulation for the F-goals model.
just one model had any surprise to it, you know?
So yeah, I've also noticed that this particular model for other analysis, not just for circulation change, but even for like our ITCZ analysis, or just looking at the moisture trends, tend to behave anomalously. So it's probably something wrong with the model physics, are very different in model physics.
Yeah, I've heard that was an outlier over years. Very good.
Yeah.
Very interesting. Thanks for sharing. I'm wondering if this is mostly dominated by the Pacific Basin, because that's like the biggest single entity on the globe. Or have you looked at it all as a function of longitudinal bins?
Yes. So if we look at, are you talking about the ITCZ?
Yeah.
Yes.
The zonal-mean
Mhm.
migration.
So if we look at the ITCZ specifically, we do find a statistically significant shift in the Eastern Pacific, where we have the single ITCZ instead of the Western Pacific, where there's an SPCZ extension. So this significant shift comes from the Eastern Pacific box. Yeah, that's about it. But yes, I guess depending on the how these models simulate their SST pattern in the East Pacific, due to their cloud simulations, which contribute to the SST pattern, can result in the double ITCZ bias. But we do not find a very strong correlation between a specific model's double ITCZ bias versus their ITCZ response to this period.
I guess to keep asking, like Tyler's been looking a lot at the Atlantic, and it seems like there the heating of the southern Africa is affecting the regional circulation. Do you see a different? Does the movement of the ITCZ over the Atlantic also follow what you see locally in the zone?
I do not remember it off the top of my head. But yeah, I can get back to you with those basin specific ITCZ results. Yes. I do remember it for the East Pacific specifically, but it's the Atlantic one, just looking at the Atlantic one. I had a question.
Oh, I was just wondering if there's a correlation with El Nino.
So we do find that for that one specific event in 1998, we do find a strong southward shift of the ITCZ, which works like Adam et al. 2016, I believe. They had two papers. The first one showed that this 1998 showed a difference in how the ocean heat uptake responds for a strong El Nino versus a strong La Nina case, and for this specific 1998 El Nino, a larger ocean heat uptake contributed to a southward migration of the ITCZ. But this relation between the ITCZ versus the ENSO index is more prevalent or more stronger for the seasonal ITCZ rather than the annual mean ITCZ. So if you were to take just June, July, August, or September, October, November, the correlation would be stronger and more significant rather than looking at your annual variations versus ENSO index.
Follow-up question. Do you think there's some connection then between chapter 1 and chapter 4, where in chapter 1 you show La Nina-like pattern change, and then chapter 4 maybe there's some connection between ENSO and the
Also, maybe the ENSO is driving this northward shift.
No, yeah, I don't know. Or like there's a more El Nino-like pattern that it's easy maybe use on southward. La Nina-like maybe more.
I mean, I would guess so, depending on how these incidents, but the big ones, contribute to the ocean heat uptake from surface heat fluxes, it would shift the ITCZ because again, the ITCZ depends on this cross-equatorial atmospheric direction transport. So big ones could contribute to shifts in the ITCZ. Had the recent uptake in northward migration of the ITCZ could it be attributed to itself? That I'm not sure about. Or how much of an effect do incidents play in this recent higher magnitude of ITCZ shift? But yeah, that'd be really interesting to look at. Because that would of course control the ITCZ pattern and then the ITCZ migration.
Thank you, Sisam.